always fun. It is always fun to come to the Latin crypt community, and I also was in the Ascrypto, I think the first edition in Sao Paulo, actually in Campinas, but because
That's
at the end, I think it is. I have a love for cryptography, and I like Latin America, as I guess that we're going to discuss later. So combining the two is always a good idea. So I'm going to start today on format preserving encryption. So let me just start sharing the slides. Hopefully I'm sharing the correct thing. Do everybody see the slides? I will assume yes, nobody.
Yes, we can.
So just a second, if you have any questions, so first of all, don't hesitate to ask them. Just unmute yourself. It would be nice if you give me a head warning, like turn on the camera and wave so I will know that you have a question, but feel free to just barge in. It's not like Israelis are well known for being polite, or you can just write them in the chat. I will try to address them, but trying to address for everything to compensate for everything is a bit complicated. One thing I have to apologize in advance. I am currently the program chair for Eurocrypt 2022, and we just had a deadline a few days ago. So this put a lot of strain on me, as well as some new things I have to do at the university due to various reasons. To avoid becoming the head of the department, I had to accept other tasks which are very time consuming. So the slides were made over the last minute. So I'm terribly sorry, first of all, if there are mistakes in them. And second of all, there are very few figures and images. So I will try to be as clear as possible. My sincere apologies, and I'm really, I would like to apologize for not making it a bit earlier. Okay, so here's what we're going to discuss. Just a second. So a very quick introduction what format preserving encryption is, and I guess most of you know what block ciphers are, but why do we need format preserving encryption? What were the early solutions? And of course, the facial-based construction, which is today all the solutions that are in standardization in use are actually facial-based, and I will explain why this is the case. We'll discuss some issues with the early solutions and why we need the FFX mode, which is facial with tweaks. And then I'm going to quickly suggest two ciphers just to show you how they look like. The FF3 block cipher, which is a standard, used to be a standard by NIST, and then the Phi family of block ciphers, which is a Korean standard. All of them were submitted for standardization in ISO, and then I'm going to tell you why it didn't go very well for them. And then I'm going to discuss some previous attacks on format preserving encryption, some basic observations due to Patarin or already from the early 2000s, and then some other attacks that were developed over the years. And then at the end, if we'll have some time, we'll go into some new results. Some of them have been accepted and are going to appear in 2 weeks at Eurocrypt 2021. 2 of them are from a different paper, which has been repeatedly being rejected. And I'm completely happy with that. Obviously, it's okay. It happens. Papers get rejected, even if the committee should have accepted it. Okay, I'm kidding. Everything is fine. This is part of the game. So first of all, a quick definition of block ciphers, just to remind you what we're discussing. Block ciphers are actually families of pseudorandom permutations. So we have plain texts, usually of n bits. We have keys, usually of k bits. So you take a plain text and a key and you generate a ciphertext. And actually so there is one issue, which is we need that for every key in the key space, the encryption is actually a permutation. And there is this pseudorandom permutation thing, the pseudorandom property, which actually suggests, it's very hard to define it from the point of view of theory, in the sense that defining a pseudorandom permutation is a bit hard, because I need to distinguish. If you think of the standard definitions of how we decide something is hard, you say it is very hard to distinguish between these two instances, a random case and this specific random permutation. Now, if you give me a specific random permutation, I can, and you say, are are you sure this is so? Sorry, the game is as follows. Somebody picks at random and he says it's either a random permutation or a specific permutation. Let's say AES with the key 0. So what I can do, I can probe the permutation on my own with some plaintext or some input, see what is the output, and then go to the oracle and ask him, can you please give me the answer to this query? Obviously, with very high probability, if this is a random permutation, I'm not going to get the answer which is corresponding to the pseudo-random permutation. So there is a bit of a trickery here when we do it, but for the purpose of our talk, and I think that from security, practical security point of view, we can say that we can't find any structural properties or impurities in the permutation, so there are no statistical significance. It looks to us random, and I'm not going to define it looks to us random. I'm just going to assume that you understand what I'm saying when I say it looks random enough. Obviously, there is some black magic here, and you need the keys to define it formally correctly. So, as you probably know, block ciphers have been studied since the 70s. They are widely used throughout cryptography and security. I mean, this conversation, this lecture is being encrypted using a block cipher in some mode of operation. So it is used in anytime you communicate, anytime you store things, even very lightweight environments. I mean, we can do today encryption for NFC devices. We have encryption algorithms that go into 400 gate equivalent, 500 gate equivalent, and give you very high security. Things like Catan or Print Cipher or Present, they exist. And you find them even in some more advanced cryptographic schemes. So today we discuss a lot zero knowledge proofs and fully homomorphic encryption and multi-party computation, quite a lot of works on making block ciphers actually hash functions, but based on block ciphers, which are compatible, for example, with snarks, very useful for Zcash and blockchain. There, I said blockchain. I think that we can tick this off. If you happen to have a bingo card, which buzzwords I'm going to use, you can tick off blockchain. And block ciphers are very, very efficient. So if you have the AES-NI instruction set or equivalents, of course, depending on your platform, it can take less than 1 cycle per byte. Now, if you think of the penalty for having a cache miss from your RAM, it takes more time to bring the page from RAM into the level 1 cache than it takes to decrypt it. So it is very efficient, and there are many good block ciphers to choose from. AES, if you need that, or Present, or many good ones, and there are even many secure implementations. So as you probably know, it's not just a matter of having a good algorithm, it's also a matter of secure implementation. Again, if you have the AES-NI instruction set, you're protected from many timing attacks and that sort of stuff. So that's it, right? Everything is encryption has been officially solved. Thank you very much all for joining me today. It was a pleasure. We can move on to the Ask Me Anything session, right? Okay.
Oh,
so, yeah, I'm sorry. Yeah, I'm asking questions and I hope somebody answers. So the thing is that think of a system, think of a real life system or a real life protocol, and it already exists. And now you need to add encryption. And here's the tricky part. Because think, for example, of a database that stores values. If we're going to encrypt the values which are stored in the database, we need to change the database. We need to change the way the database works. So if, for example, and the canonical example is credit card numbers, there's also social security numbers. So let's assume that you do have a protocol that broadcasts credit card numbers. Now, as you probably know, sending unencrypted credit card numbers is a very bad idea. But I have a device that reads my credit card and sends it to some server, and the protocol was defined in the 80s or the 70s or sometime later, but nobody thought of the fact that credit cards are actually blobs of information that you need to encrypt using a block cipher or using something. So from their perspective, you're supposed to submit 16 digits, or you need to store 16 digits. And there's also some sanity checks. I guess most of you know that credit cards, the last 2 digits are actually sort of error detection code, and from our perspective. So I must take a credit card number and return a credit card number, because otherwise the system will break. Now, I don't know how many of you were around during the 2K bug, where everybody was sure that the sky are going to completely fall on our heads and planes are going to crash. And it took them only a year, 9 months and 11 days later to crash on the World Trade Center. But at the end, we were afraid that the world is going to collapse because someone in the 60s or the 70s decided to encode years using 2 digits to save space. Now, for many of us today, this sounds like, why would somebody want to save space? Like, we're using stuff which is completely impractical for old systems, but this was the case. So here's the problem. Either we rebuild the infrastructure of all the credit card and social security numbers and all this jazz, or we somehow encrypt a credit card number into a new valid credit card number, different one. So when it is transmitted, nobody is going to learn anything about the real credit card number. Now, if I will take the credit card number and I will encrypt it using AES, for example, the chances of getting a valid credit card number is so small that I'm not going even to compute it. You can compute it as an exercise at home later. So what Brightwell and Smith suggested in '97 is that actually, in order to make cryptography more prevalent in systems, we need the ability to encrypt non-standard domains. Now, one issue to note, and I'm going to address it a bit later, is that the size of the domain may be very small. This has a very big impact on the security against various attacks that usually when we think of AES, they cannot be made. But when you have a small domain, you can actually do that. So the first example of such a cipher was the AES candidate Hasty Pudding by Rich Schroppel. It's actually an ARX construction. If it tells you something, it's okay. If it doesn't, don't worry, nothing bad happens. It's actually 5 ciphers depending on the block size. So there's Hasty Pudding tiny, Hasty Pudding medium, Hasty Pudding large, extra, 5 different ciphers, all of them with the same name. It can encrypt any number of bits, but so it's also one of the first wide block constructions, if you know what wide block ciphers are. There were security issues. There are some equivalent keys. It has performance issues, especially and especially implementation issues when you have 5 different ciphers that all of them are hiding behind a single name. Obviously, there are going to be issues, and also it cannot handle non-binary domains. So it has to work with a fixed. It has to be a fixed length of binary strings to be encrypted. So by the way, Hasty Pudding didn't survive till the 2nd round, even though it brought something interesting to the table. So a bit later, Bellare and not Rogaway, I will remember who is the R. I'm terribly sorry. Suggested 3 solutions to how to build format preserving encryption for any domain size. So the first one is the cycle walking. The idea is as follows. Let's assume that there is a larger domain, D prime, for which we have encryption. So remember, our task is to encrypt things in a smaller domain. So we take a larger domain for which we have an encryption. So think of, for example, taking 96-bit strings and trying to encrypt them using AES, which has block size of 128 bits. So what we do, we take a plaintext, and then we iteratively encrypt it until we reach another value which happens to be in the domain. So if the ratio between D prime and D is very close to 1, then usually we're going to do 1 encryption, and then immediately we're going to get something which is good. Otherwise, if the ratio is very high, like in the example I gave you, you will need to do 2 to the 32 steps until you encrypt 1 value to another value. Is the construction clear? Are there any questions about the cycle walking? Yes, no? Francisco?
I have one question.
Yes.
Or this formal preserving encryption was proposed in 97, back in 97, as you said, 2 slides before. But there was, by the proposers, there was no instantiation of their idea. It was just a theoretical.
Yes.
Oh, okay.
Not a theoretical. Ernie Brickwell used to work for Intel, so he spoke about problems from real life. Like, this is what practitioners in the field need. And I remind you, this is 97. I guess most of you, again, if you remember how computers used to work in 97, the internet was just starting to really catch on. Most people didn't have internet connectivity. It's still, there is an issue in some places, but there was no big internet. There was no SSL3. I think SSL3 came, sorry, there was already SSL3, but it came a bit, not much earlier. And most of the systems were designed, I remind you, 97, most of the systems were still COBOL systems running, and they were designed in the 70s and implemented in the 80s, best case scenario. So there was a real need for that. Now, the thing is that today, because, and the protocols also that were designed back then and we're still using them, also need format preserving encryption. So you see this a lot. Actually, it is used a lot in the finance sector and very old databases, but they are very crucial and critical databases which you cannot touch. You don't want to change Visa's credit card database to support encryption now. I mean, we do want to do that, but they're very reluctant to do this sort of change to their infrastructure. So Ernie was raising an issue from real life, but he didn't have a cipher that could do that. Okay. So the cycle walking is very simple. You start with a plain text, you encrypt it iteratively until you reach a point which happens to be in the domain, and this is the ciphertext. A very simple cipher. You can easily prove it is secure. Of course, you cannot. If the cipher in the larger domain is a pseudo-random permutation, then the cycle walking is also a pseudo-random permutation. All the theoretical requirements are being satisfied. There are two issues here. First of all, the time is far from being constant. I never know when I'm going to hit the next value. So for some plain text, it's going to be one step of encryption. For some others, it's going to be 2 or 5, or it can be more. And even if D prime and D are very relatively close, you still may walk quite a lot of time. And this is a bit of an issue. Besides of being a side channel issue, it is also an operational issue, because if you have a blocking call, you don't know when it's going to end. So it changes a bit timing and causes a lot of problems in asynchronous world. Another thing is that if you have two domains which are related somehow, D1 and D2, both of them being embedded into the same D prime, you may be able to learn something about the encryption in D1 by looking at D2 and vice versa. So I'm going to show you later some interesting related domain attacks, but this is a real issue here. Okay, so here's another construction. This one doesn't have this problem, but it requires a lot of memory and a bit of pre-processing. So here's the idea. Let's assume that the domain D has T elements. So again, you pick D prime, which is larger, but it can be any size. I mean, it can be even like completely unrelated. And what you do, you compute a sequence of numbers, A0, which is the encryption of 0, A1, which is the encryption of 1, etc. T time, you get T values. And then you sort them. Now, the thing is that because this is a random permutation, a pseudo-random permutation, the sequence is going to be random. I mean, everything is going to be roughly the same probability, so everybody should be happy. And how you encrypt? So you find the order of P in D. So you just count. Let's say the domain D has some order. And when I say order, I don't mean, sorry, the order in a subgroup. I mean, order in the domain. There is some lexicographical order there. And you find it, you call this value J. Now, you go and you look for AJ in the sorted list. So if, for example, we try to encrypt the value 1, and because the counting starts at 0 here, so this is the second value. So we're going to find A2 in the sorted list of AIs. So if, for example, A1, which is the second value, happens to be in location 55, that means that P was encrypted to the value which happens to be in location 55 in the original domain. And that's it. Very simple. It takes constant time. You just need to pre-compute this table once because you cannot do random access here because you need to sort. Okay, everything is clear? Yes.
Can I have a question? So
yes.
Maybe I should have thought of this before, but is encryption deterministic?
Yes, we were discussing deterministic encryption. This is like the late 90s, beginning of 2000. Everything is deterministic. And besides, usually block ciphers themselves happen to be deterministic. You need the mode for generating the randomness here. Now, specifically here, you have keys. The keys generate the randomness that you would expect. But yeah, everything here is deterministic.
Okay, but if you then encrypt twice the same,
it's going to be the same. Unless you change keys. If you change keys, things, but from a block cipher's perspective, when you send a credit card number, you buy twice using the same credit card, you should get twice the same ciphertext. I'm going to discuss this a bit later because as you mentioned, there is an issue. There is an issue that stems from that fact, that it's deterministic. Okay? Carla?
Yes.
Okay. No, okay, I'm sorry, it's just that I have a very limited view of who is talking. Okay. And the final construction, you take the domain D and divide, and let's assume it's n times m, and you just take the plaintext P and you divide it into two halves. One of them is from Zn, the second one is from Zm, and you just run, yeah, Black and Rogaway. Thank you very much. Yeah, it's not Belar. The thing is that Belar and Rogaway worked a lot and together. So whenever I see BR, it's automatically Belar and Rogaway, and I remember it's not Belar and Rogaway. I assumed it's so it's indeed Black and Rogaway as I think it's almost suggests. Yeah.
Yes, that's okay.
Okay, so again, you just separate it into two halves, PL and PR, and then you divide it into two halves, and then you run a facial construction. So the right half goes into the round function. It is modular added to the other side. So because one of them is modulo M and one of them is modulo N, and I may have swap the order. It's always confusing which is the left and which is the right. Yeah, of course, I swap them. This is N and this is M. So you add here, then you're doing a modular addition, and then usually for FPs, we don't do the swaps of facetals because one of them, they are usually different sizes. So it's just not to confuse. One side is modulo M, one side is modulo N, and that's it. And you just repeat it as many rounds as you want. And this is the facial construction, and everybody are happy. Everybody are happy? You're not happy. Okay, so there is one problem, and it relates to what Carla mentioned before. If you have a very small domain, you can enumerate all the plaintext ciphertext pairs for a given key. That means that when I'm using the credit card again and again and again, it's going to be the same ciphertext again and again and again. And information about the fact that I bought 5 times in this shop in the last 24 hours is going to be available to the adversary, even though he doesn't know what is the credit card number. He knows there is someone who bought 5 times using this credit card number. So there is an enumeration possibility here. And the solution for that is to add tweaks. So here is the FFX mode of operation. You will be surprised to see this is just, again, everything is now based on the facial construction. We just add tweaks in each and every round, and the tweaks generate the randomization. Now, tweaks, if you don't know, tweaks from trickable block ciphers is some public parameter which diversify the encryption process. So for example, for the case of format preserving encryption, instead of always encrypting the same credit card to the same value, you get something which is which is slightly different depending on the tweak. So the tweak, for example, can be the station number and the time of the day. As long as both sides know it, everybody should be happy, and all the enumeration attacks break, assuming that you have enough tweaks. Okay, so here's an example by Brière, Perrin, and Stern from 2010, FF3. It was first suggested as BPS, but then renamed for FF3 by NIST. It's an 8-round facetil. The key size is 128-bit. The block size is up to 192 bits. You take essentially you break the plaintext into 2 halves. You try to make sure they are roughly the same size. And then you just use the following round function, and the key argument, the key element here is that you have a full AES 128 under the key K as the round function. So you take the right half, you encode it in 96 bits, you add a tweak XORed with the round constant, and which are encoded in 32 bits, and then you encrypt using AES 128, and this is very secure. The next round you do the same, the slightly different part of the tweak and the round number, and you just repeat it 8 times. So actually these 2 rounds are repeated 4 times in total, and this was part of the NIST special publication 838G for format preserving encryption together with FF1. FF1 is very similar, it's just that the round function is you just compute hash of the tweak and the key and some other parameters. And then you add it to the other side. So FF1 is slightly different, and it has 10 rounds. But this is how it's going to look like. So I guess that you see that it's very nice and very simple. You just need an implementation of AES. Each block costs 8 invocations of AES, but you don't need to recompute. The second example is the phi block ciphers. It's a family of block ciphers from Korea. These are from the Korean standard, originally designed by Lee et al. From 2014. They support 128-bit key, 192-bit key, or 256-bit keys, and the block size from 8-bit to 128 bits. It has to be, unlike FF3 that you can do almost anything, which is reasonable. Here it has to be an integer number of bits, and you divide it into 2 equal halves, or if the number of bits is odd, one of them is 1 bit extra than the other. But this is exactly the same round function. Everything is the same. I mean, as you can see, it's not very interesting. I would mention several elements here. They're in the slides, those of you who want to see it later. First of all, the expand is just concatenating X with the tweak. This is the expand function. This is a subkey. This is a subkey. These are the AES S boxes. This is an MDS matrix. So what happens, even if you change a single bit here, you have 1 active S box here. If you know what active S boxes is good. If not, just wait till the end. And then because of the MDS matrix, you're going to have all these S boxes active. And then there is another MDS matrix, and then you truncate. You just pick the n bits that you need to pick for being added to the other side. So a very nice function, very efficient. I mean, this is like half a round of AES or 1 round of AES, so you can do it significantly faster. And because of that, you have stronger, faster, and so you can do more rounds. One thing to note, there is a key schedule algorithm. It's very complicated, but each round you need 128-bit subkeys. The tweak schedule for phi1 is actually the tweak left, tweak right, tweak left, tweak right, very similar to FF3. For phi2, they use something slightly different, which looks kind of weird. 0, tweak left, tweak right. 0, tweak left, tweak right. Actually, it's surprising, but this looks like something weird, but it makes the cipher immune to some of the attacks I'm going to discuss a bit later. So something that looks completely weird actually makes the cipher significantly stronger. Okay, so this is the world from the construction part. Now let's discuss the fun part of destroying things. So first of all, do note that the round functions are non-bijective. Just to clarify, once you start truncating bits, I mean, if I didn't have to truncate any of the bits, and I stop here, sorry, somehow the annotation disappeared. if I stop the computation here, the round function is bijective. But when I start to truncate bits, I get something which is actually a random function. So the round functions are random functions and not random permutations. And I need all of you to agree with me on that part, because otherwise we can end the talk now. Okay, we all agree it's a random function? Speak now or forever hold your breath, or wait for the Q&A at the end. Okay, good. So we all agree this is the situation. So that means that if you put some input difference into the round function, with probability 1/n, you're going to get a 0 output difference. And this is very unique. If you think of most of the modern block ciphers, we try to make sure that differences, input difference, non-zero will not cause a 0 output difference. In this happens due to various reasons, and the best known attacks against this are actually exploiting this fact. Now, starting from this point, most of the time I'm going to just, let's assume that both sides are n and n, the domain sizes are the same, just to make things easier. Otherwise, we're going to have n, m, n. Yeah, I know that it's a bit complicated here. Let's stick m equals to n, so I'm just going to say 1/n, and that's it. So this is the round function, and it causes differences, input difference, which are non-zero to become 0. So this allows me to build an iterative differential. So think of someone starting with a 0 difference 0 here and a delta 0 here. And here, let's say the first round function is like that. So 0 input difference will always cause a 0 output difference. The delta here is going to go and have probability with probability 1/n, output difference 0. So this 0 maintains. And then again, 0 goes in, 0 goes out. Delta goes in, 0 goes out with probability 1/n. And if I repeat this r times, the probability of the differential is sorry, not 2. You haven't seen the number 2. The number 2 doesn't exist. The probability is 1/n, r/2. Right? Wrong? Let's try to do something. Those of you who are in favor of what I just said, please raise your hand. Those objecting, please raise your hands. Those who think that raising the hand is a bit too complicated, raise your hands now. Yeah, okay. Yeah. I get it. You don't like raising your hands. Anyway, this is the case. You can check it, and you should all be very happy. But there is just a slight technical detail. I forgot to tell you something. You see, if you look at FF3 with 8 rounds, the probability is 1/n4, n to the power 4, right? 8 rounds. This is what we just said. The number of rounds is 8, so there are 4 times the transition. The probability is 1/n4. There's one small technical details. If I would have taken a random permutation, and I would ask myself, what's the probability of starting with a 0 delta input difference and ending with a 0 delta output difference? The answer would be, drum roll, you can write the answer in the chat. While you're writing and you're doing the computation and writing the answers in the chat, I'm going to surprise Francisco and mention the fact that I still hold this wonderful certificate. I don't know if you recognize this. I don't see answers in the chat. For everyone else besides Francisco who can look and try to remember what this is. All the rest need to write the answer. What is the probability of the transition for a random permutation? The answers are in. Nobody answers. Okay, let's start again. What is a random permutation? Look, I give you a plain text P, right? I give you a plain text P, and I'm throwing it into some random permutation. So I'm getting a ciphertext C. What is the probability that I take P prime, which is P with some difference, delta concatenated with 0, and I throw it through the same random permutation, and I get C prime, which happens to be C XOR the same constant. And for that argument, it doesn't really matter XOR what or addition with what. Come on. I remind you the domain size is n squared. Yes, thank you, Carla. Indeed, if you have a condition, look at the condition from the perspective of the differential game. I ask you the question, what's the probability that I take P and P prime, some two values that I defined somehow, and that their ciphertext satisfy some condition, let's say n over n squared values. So once this ciphertext is being fixed, there are actually the probability, if I want to be accurate, is 1 over n squared minus 1, because there are n squared minus 1 possibilities for C prime. And I'm asking what's the probability for this random permutation that P prime actually became C prime. So, and I'm going to disregard this factor minus 1. So for a random permutation, this happens with probability 1 over n squared. So I found a differential characteristic which happens with probability lower than in the random case. Yeah, this is not useful, right? I'm going to stop speaking until someone tells me if it's useful or not. In theory, it shouldn't be useful, because in differential cryptanalysis, if you remember, we're trying to find something which probability is high as possible. And the reason for that is that if it happens in a random permutation, then we cannot distinguish between a random permutation and the cipher that we're working with. The thing is that actually for FF3, the real probability is about the random probability plus this additional factor. And this we tested. I can do the full theoretical analysis. The tests agree with the theoretical analysis. You get the random probability plus a small advantage. Okay, now I'm not going to ask you again, because I think that for most of you it's too late. The amount of data in the number of pairs I needed in order for me to verify whether the probability of the transition is 1 over n squared or 1 over n squared plus a small advantage, this probability is actually the number of values, the number of pairs I need is about order n to the power of 6. Here's the thing. When you look at a single key, and if you don't have tweaks, the plaintext world is composed of n squared plaintexts. Luckily for us, there are tweaks. So we can obtain still order n to the power of 6 pairs by just using multiple tweaks. And this is something that Patara already observed early in 2001. And how are we going to use that? So here is a message recovery attack. This time I'm sure it's Bellare, Hong, and Trio. And here they describe a weird game for cryptanalysts, but here is the thing. I'm holding in my hand a special plaintext X prime, and I'm holding a second plaintext X. Now, I'm telling you X prime, so you know L prime and R, and X has the same right half, but a different left half. And I'm not telling you L. And the game is as follows. You can come to me and tell me, or please encrypt me, for me, X and X prime under different tweaks. And I'm giving you ciphertexts. Now, remember the differential characteristic I've shown you earlier? because there is a small bias, if I look at the ciphertexts, there is a small bias that the difference between the left halves of the ciphertext is going to be slightly biased towards the difference between the left halves of the plain text. So for the FF3, I need order of n6. In the case of FF1, I need order n to the power of 8 to identify whether the bias exists. And once the bias exists, I know exactly what is the value of L minus L prime or L prime minus L, which if I know L prime allows me to get L. So this is a weird message recovery attack, but it works. And from their perspective, they shown that for very small domains, for example, for 4-bit domains, if you're allowed n equals 16, their attack was something like 2 to the 24. Now I'm disregarding small constants here, and I feel that I'm a bit cheating because there are sometimes constants here, but at the end you find them, and usually they are not very large. Here, for example, there is a factor 6, which I neglected for a second, but for the sake of argument, it's 2 to the 24. Now you can say, oh, what are we going to do? So here's the NIST solution. N has to be at least 1000, and therefore an attack of n to the 6 is 1000 to the power of 6, which is 2 to the 60. You're not supposed to get 2 to the 60 ciphertext pairs in format preserving encryption. Partial solution, but this is their claim. Okay. Now let's move on to FF3. FF3, and I remind you, has a very simple tweak schedule, and this is a paper by Durack and Vadonnet from 2017. And this is the round function, and the round number starts from 0. Okay. How many of you would prefer the round number to start from 1? Come on, everybody. I know it's late. I know it's hard, but do you prefer? Those of you preferring that we start from 0, please do like that. Those of you who want to start counting from 1, do like that. Those of you who hate counting for any reason, just tweet something about that. Please. I'm trying to get, I see some people in favor of 0. Yeah, no, I don't feel any strong reaction to any of the 0, 1. Okay, but 0 is a bit more popular than 1. I just want to mention the following fact. The following attacks that I'm going to describe work just because they started the counting from 0. If they would have started the counting from 1, these attacks wouldn't happen. And this has to do with the following weird phenomena called carry. You all heard about it in 1st grade or 2nd grade or 3rd grade, depending where you studied math, arithmetics. But apparently, if you take 2 tweaks, TL and TR, and T prime, which is TL XOR 4, and TR, which is XOR 4, you get the following 2 things, and I hope that you see this. The encryption under T, the tweaks is TR XOR 0, TL XOR 1, TR XOR 2, TL XOR 3, this is just counting, and XOR 4, XOR 5, XOR 6, XOR 7. In the right-hand side, I remind you, we picked the tweak was TR XOR 4 and T left XOR 4, right? So this is TR XOR 4, this is TL XOR 4 plus 1, which is TL XOR 5. And this is plus 2, and this is plus 3. Again, with very high probability, I'm disregarding here a few small things, but it works. The interesting part is that what happens in round 4, because we started the counting at 0, because you preferred starting the count at 0. This is your issue. You guys should have voted for 1. So in round 4, here we get TR plus 4. Actually, it's everything is XOR, and here it's XOR 4, XOR 4. What happens when you XOR 4 to itself? Disappears. So you get here XOR 0, XOR 1, XOR 2, XOR 3. So if I call these 4 rounds F, and I call the last 4 rounds G, the encryption under T is composed of F and then G, and the encryption under T prime is G and then F. And it would have been solved if you started the counting at 1. Okay, so we get actually a slight property. Now, throughout the remainder of this part, I'm assuming it's the same key always. Just disregard the key. There is a key there. Everything is a keyed function, but I am not going to mention it. So what I'm going to do, what the attack does, it recovers the round function. So generally speaking, encryption under T is F and then G. Encryption under T prime is G and then F. Now, what happens if by any chance P was encrypted again, first under F, we got P prime, and then it encrypted under G into ciphertext C. And at the same time, I took the same P prime and encrypted it under T prime. So the first 4 rounds are going to be under G, so they're going to be C, and then the next 4 rounds are going to be F, and we're going to get C prime. And this is a slide attack. Those of you who know slide attacks, this is exactly the issue with slide attacks. And the interesting part is that I can continue, because if C after F becomes C prime, so if I will continue to encrypt C, I'm going to get here another G, which will be, let's call it C prime prime. And C prime, if I continue to encrypt it under T prime, I first start with G, so it's C prime prime, and then another F, which will make it C prime prime prime. You see, I started the counting at 1 prime, then moved to 2 prime, and then 3 primes. Start the counting at 1. So this actually generates a chain of values. And the interesting thing is that the chain of values, earlier I had to break 8 rounds of a facetel. But C and C prime are just 4 rounds apart. P and P prime are 4 rounds apart. C prime and C triple prime is 4 rounds apart. So suddenly I don't have to break 8 facetel rounds. I need to break 4 facetel rounds. Okay, so this is the main observation that everybody are using. And because we don't have a lot of time, I'm not going to go into all the technical details here, but we're trying to break 4 round facetel, where each round is a full AES. This is a bit complicated. Luckily, what happens is we're going to take chains of values, and we're just trying to find whether they are generating something that works. So we have the main idea behind the attack is take many P and P primes, generate from them chains, and try to check whether the chains that you generated correspond to 4 round facetel construction. If this is the case, you found P, you find P prime, and now we just have to attack 4 round facetel and reconstruct it. I would just want to mention the fact that if P and P prime are random, then the probability of the condition to happen is 1 over n squared. And that means that I need to do n over n squared pairs of tests to work. So this is actually the attack. They have a procedure. I'm going to discuss it in a second. And they're just going to try n squared locations, and for each of them run an attack that takes n to the power of 3. So the 4 round procedure takes order of n to the 10 over 6 known plaintext. And this is one of the reasons they had to change Pataran's attacks, is that Pataran uses chosen plaintext, and they needed a known plaintext variant. And there is an efficient way to generate the chains. You just generate n over 6, n to the 6 chains. Each of them are very long, and then you try all the respective locations and offsets and all pairs. So you get the locations. And the 4 round reconstruction is a bit technical, so I'm just going to give the main idea. We look for the case if this is indeed 4 round facetel construction. These are the relations that happen. This is just writing down the encryption and calling the values left, right, I mean, just like they're supposed to be. And if everything, and what we're looking for is cases where we have 2 plaintexts, 2 inputs, which share this value. Now, if they share this value, they share this value. The F0 is the output of the first round function, the F1 is the second round function, etc. So if these are the same between 2 plaintexts, these are going to be the same over 2 plaintexts. And that means at the end that the difference between the outputs of F0 is the outputs, the difference in the inputs here. Because if you trace back everything, this is the condition. I'm not going to do that, but this is the case. So again, you will have to trust me on that, especially as we have about 10 minutes, right, Francisco?
Yeah.
Okay, so the idea is that you take the chains. I suspect that these chains are correlated by 4 rounds shift. I extract all the, I pick all the locations which are good to me, and then I extract this condition because I know the inputs, I know the inputs, and I just get the condition on the outputs of the first round function, and I try to solve this. How do I try to solve this? For example, I'm trying to find sets of inputs, for example, F0 of some input 1 minus of F0 of input J. I know the value, and then I get another equation of the forms F0 of J minus F0 of some T is equal to something, and then I get F0 of T minus F0 of I is equal to something. So this is called the cycle. In this specific case, it's of length 3. And this is the important part, because if you sum all these equations on the right-hand side, you will see that I always have 1 in plus and 1 in minus, so the sum has to be 0. Then the sums on the left half have to be 0 as well. So the idea is find many cycles that the sum, that when you add them together, you get 0. And then you get many equations, and from that you try to reconstruct the round function. So how do you find the cycles of length 3? And this is the easiest solution that they used. They just use Floyd-Warshall algorithm, order n to the power of 3, and you need to call this n squared times. So the data complexity n 11 over 6, time complexity n over 5, and the memory complexity n over 11 over 6. You have to store the data. So this was the result. And as a result of this attack, NIST decided to tweak the tweak algorithm. You can no longer play with this XOR 4. The area where you need the 4 is always, the tweak is set to 0. They actually reduced 4 bits from the tweak on both sides. A bit later, in Encrypt 19, there are several improvements. The first one is a better identification of the locations. And the second one is a better graph algorithm. Main idea is that if the F parts, if they're one F part, they're just 4 round facial apart. Now we have better distinguishers for 4 round facial than trying to solve the equations. So earlier, for each possible location, we had to do a reconstruction. Now we don't need to do a reconstruction for all the locations. First of all, we found locations which may work, and only then we reconstruct. So the idea is, what distinguisher for 4 round facial did we already see? The answer was in the previous slide. Great. It is indeed a differential. If you look for 4 round FF3, the probability of this differential happens with probability 2 over n squared instead of 1 over n squared. So what they do, in a very nice, using hash tables and a very simple and efficient algorithm, they try many locations simultaneously and test whether there are 2 over n squared or 1 over n squared. But they do it in many locations in parallel, and then test in how many of the locations they think this is the case and how many locations they think this is the case. I never really got that idea. And as a result, they're able to reduce the number of locations. Instead of n squared locations, they have only order of n locations to test. So, and they can do it in this is 2 5 over 3, 2 and 5 over 6, sorry. So this is n to the power of 2.8 or something like that. Yeah, and there is, as I said, this is a kind of weird. If you do cryptanalysis, you will look at this and say, somebody here didn't do thought until the end. And their way to find cycles of length 3. So earlier they used Floyd-Warshall. Now they say, a cycle of length 3, you take an edge, and because the edge defines the two values here and here, it also automatically defines the value here. So you just go and check whether this value happens to close the cycle. So instead of spending a lot of time on Floyd-Warshall, you just spend the time which is significantly smaller, and the result is this is the complexity of the attack, and everybody should be happy now. Everybody are happy now? We're getting close to the end. So, okay, so I'm going to rush through our improvements. First of all is how to do it better, and this is a paper to appear in 2 weeks with Ohad Damon, Nathan Keller, Eyal Ronen, and Adi Shamir. These are 3 new attacks on FF3. Everything was experimentally verified. Everything works. And one thing about Hong et al. Paper is that they took many experiments, which at the end, if you look underneath all the calculations, this is a Poisson random variable. And they had 2 experiments. Either this is a random permutation and you get Poisson with a mean value of 1, or this is 4 rounds of FF3, and then you get something which is Poisson with mean value of 2, and you repeat it many times, and you test how many times you succeeded. Now, counting the number of successes when you do it this way, work using Chebychev inequality. I'm not going to remind you what Chebychev inequality, but I'm just going to mention there is something called Chernoff inequality, which is completely better. Specifically, if you sum several Poisson distribution, you get a Poisson distribution. Now, the thing is, the variance of a Poisson random variable with parameter lambda is lambda. So the statistical difference here is very small when you count standard deviation units. However, if you pick C to be very large and you try to distinguish between Poisson C and Poisson 2C, the distance here in standard deviation units is significantly larger. And because you're trying to distinguish between 2 distributions, you want the distance to be as many standard deviations as possible. So this is something that you can easily do, and you get a significantly better distinguisher. Indeed, a significantly better distinguisher. So actually, we can reduce the data. And we also get some data time trade-off, but I'm not going to discuss it now. We can take shorter chains, and we can take slightly more chains, but shorter ones. So everybody should be happy. The cycle finding, I remind you, we need to, this is a problem in graphs. So we need to find cycles of length L in a random graph. And in our parameters, there are about order n nodes, and each of them has an average out degree of order n 1 over L, where L is the length of the cycle. What the original solution was Floyd-Warshall. HMT solution was to find an edge and then trying to close the cycle somehow. We use something significantly easier. We just pick a node and then we perform. We know the cycle is of length L. So we go all the possible path L over 2 steps from one side, all the possible locations L over 2 steps to the other side, and try to meet in the middle. And this gives significantly better cycle finding algorithms. So the results, because of that, we are allowed to use L equals to 4, which allows us to reduce the data complexity even more, and everybody should be happy. Here is the comparison. I just discussed the symmetric slide attack, and you can see that we beat in every parameter, and this is even before the fact that we have some trade-off. And I think the most important thing, if you do get to the Eurocrypt paper, the asymmetric slide is the coolest one. Now, we don't really have a lot of time, so I'm just going to mention the related domain attack. So what happens if you have 2 domains, D1 and D2, which are just 1 bit apart? And I'm allowed access to encryption in both domains. And this is true for FF3 and FF31. And I'm trying to do something like that. And look, what happens is that here is one encryption. So here I had right and left. Here I had right and left. Here, this was N, this was N, this is N, and this is 2N, twice as large. Let's see what happens. If by chance I pick this plaintext to be not just any L, but 0 concatenated with the same value here. So if this is X, I go on X the same, and I want this Y, and I want this Y. Y will go to the same function in both cases with the same key and the same tweak, and I'm going to get the same output. up to the point that here I take the value modulo 2n, and here I take the value modulo n. But with probability half, I'm going to get here after the addition, and you can check that it happens with probability half. If here I get some value alpha, with probability half, I'm going to get 0 concatenated with alpha. Now, this goes into the round function of ff3, but it's essentially the same alpha because the encoding of 0 concatenated with alpha and alpha is the same. So I'm going to get the same output here. And then this is going to happen again and again and again, 4 times in total. So with probability 1/16, the encryption of 0 x, y, if this is going to be a when I'm going to encrypt x, y in the smaller domain into a wz, with probability 1/16, the encryption of 0 concatenated with x and y is going to be 0 concatenated with w and z. And 1/16 is a very high probability. I mean, it's very easy to use this for distinguishing, and you can do other cool stuff. So very easy distinguisher. And of course, the solution is the domain size should impact the rounds. For example, in FF1, part of the things that go into the round function are the domain size. Okay, we don't have time, but I'm just going to really mention that there's also issue how to make the tweaks, and otherwise you can do much better attacks. If it's TLTR, you can get better results. I'm just going to show you specifically how we break Phi1 and Phi2, which are the Korean standards. For example, Phi1 has a 14 rounds when you use 192-bit keys. So the 13 round distinguisher needs order n to the power of 10 pairs. So what we do, we guess the last round key, and we check whether the distinguisher works. This is a standard way to do differential cryptanalysis. And we can break 192-bit key in time 2 to the 136. And now, without using the tweaks, our attack needs 2 to the 32 data with using the fact that the tweaks are somehow related. We need only 2 to the 22. So the fact that the tweak schedule is not good allows us to reduce the data complexity by a lot. I just want to mention that this tweak issue also appeared in the Best Paper Award for Crypto 2021. They look at it from a linear cryptanalysis point of view, but it's essentially the same issue. And as I mentioned before, ISO tried to ISO, the International Standardization Organization, tried to standardize a format preserving encryption, but at some point during the discussion, we said, look, there are issues here, so you cannot do that. And the idea was dropped. And I think that's it. Thank you very much for your attention. If you have any questions, ask now or later.
Thank you very much, Orr, for your presentation. We have time for some questions. Anyone has questions for Orr? If not, maybe what should we do? Should we go immediately to the other session, or yes? Or let Orr to take a teacup or something that looks like that?
Maybe can I ask something? So,
yes.
Please, Carla.
So now you say, so all this, so what are the prospects for a standardization? You think this is not going to happen anytime soon? Or?
So there are several things that need to happen. First of all, the number of rounds must be increased. And second of all, they need to adapt several parameters. For example, making sure, so a design criteria should be, make sure that the domain size affects the round function. You should make sure that the tweak schedule. So we learn these design criteria. I would expect people to design new ciphers. I know that one of my students is working with me on designing a new format preserving cipher. Under these rules, we're going to try and do something better. And then it's you publish it, it goes through the community analysis, then maybe somebody would like to standardize it. Okay, It will take some time. But again, in Korea, there is a standard. In NIST, there is a standard. NIST actually said that they're not going to retract the standard. The Koreans have changed their, are in the process of changing their standard because of the attacks. But these are key recovery attacks, so from their perspective, they cannot handle that. NIST says we were aware of some of the attacks, we don't care.
Maybe the Koreans can change their name too. You know that fea means ugly in Spanish, right? So
well,
they have the chance to change the name.
You know, if we start looking at taking Korean words and saying them in Spanish and vice versa, this is not. This game is very complicated. For example, my daughter is called Liron, and my Spanish friends always make fun of it because it means that, yeah, you know, I don't have to tell you what Liron means in Spanish, but in Hebrew it means joy for me. So,
a beautiful name. I have a very quick question. You mentioned about experimentation, that it was kind of comprehensive, but yes, the numbers are huge. So can you tell us
so the numbers, they look very huge, but I think if you take a block size of 12 bits, this is the largest. So n equals to 2 to the 12. So the block size is actually 24 bits. N squared is 48. 2 to the 48. It's still doable.
Mm-hmm. Yes, yes, it is.
So, and in some cases, we did the experiments accurately. It's just that sometimes we said we're going to try it. We tested things like, instead of storing them, we just recomputed them, because at the end we have the key. So instead of having very large tables, so we use the fact that we know how to take a plain text and generate the ciphertext. Of course, not in the analysis part, but in the running part of the attack. So instead of accessing memory, because again, tables of 2 to the 48 are possible, but given the fact that the student has to be, the student who did it is being drafted next week, and we didn't want him to spend too much time on handling memory. I mean, we are cryptographers, not memory handlers. This is not like, so we allowed ourselves at some places to say, okay, let's,
okay, that reminds me another issue. You mentioned meet in the middle as one of the contributions. Those binary, Van Nostrand binary attack could apply, like this time memory trade-off?
No, it wouldn't help that much in this perspective. Especially, this is not the bottleneck. At the end, this is not the bottleneck. So for us, for a very short period of time, it was the bottleneck, but we know how to go around it. And this is why the asymmetric, I didn't show the asymmetric slide, but then you get something which is not balanced. And usually in cryptanalysis, when you have something which is not balanced, you say something is wrong. There should be balance. Cryptanalysis is like the force. There should be a balance in the force. But
okay, thank you very much. So any more questions for Orr? Otherwise, thanks the speaker again. Thank you, Orr. And then we are ready for our surprise.